Hey, what's up, guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127. In this lecturette, I'm going to cover joint probability density functions, and we are going to look into some theories associated with it. We are going to see its properties and how we can obtain the marginal PDFs of the individual random variables. We are also going to look into some methods of evaluating the probabilities of different events pertaining to joint probability density functions. But first things first, let's talk about your midterm number 3, which is going to come up on 10th April on Friday. It's going to be an open book, open notes type of exam. You can use all the possible resources except for communicating with your peers. And the submission time will be set and it will be strictly enforced to ensure fairness. So these are the items on which I will be quizzing you. I'll be focusing on continuous random variables, the probability density functions, cumulative distribution functions of continuous random variables. You may expect some questions on the families of continuous random variables like Erlang, Gaussian, to be very specific. I mean, you will definitely expect some questions related to the normal random variables. So normal random variables will be quite normal in your exam. And you may also observe questions on joint CDFs, joint PMFs, joint PDFs, and marginal PDFs, which are the agenda of today's class. So as I mentioned before, it's going to be open books and open notes, but your submission will be strictly enforced to ensure 100% fairness. So consequently, we won't be meeting on Friday for our WebEx session, but instead we'll be meeting on Wednesday, 8th of April to solve some instructional problems that will be similar to your midterm exam. Now, midterm number 3 is again optional for those individuals that have performed or that are happy with their midterm 1 and 2 performance. If you have not done well on midterms 1 and 2, then you should definitely take midterm 3. Because of this coronavirus pandemic, unfortunately, this has to be an open books and open notes, which means that it's going to be at a higher difficulty versus your previous midterms. But consequently, I'll be lenient with respect to grading. What I'll be looking into is your grasp of the concepts and your ability to apply the concepts. So even if you feel that you're not sure about the answer to a particular problem, you shouldn't worry about that much, but you should focus on getting your concepts right and trying to get your answers to correctness as close as much as possible. More on this we can discuss on 8th of April, Wednesday. So let's talk about this class's agenda, which is joint PDF and marginal PDF. So recall that the cumulative distribution function of a continuous random variable is given by capital F of x, which is obtained using the probability density function, small f of x, by integrating the PDF from -infinity to x. This concept can be extended to joint random variables comprising x and y, and now you will have a joint CDF, capital F of x, y, which is obtained by double integrating the joint PDF, small f of x, y, from -infinity to y first, and then from -infinity to x. You can also switch the integration order, that's not a problem. Joint PDF happens to be the most useful probability model for joint continuous random variables, and we will use them almost exclusively to find all kinds of probabilities for all kinds of events. Just like for your single random variable, the probability density function, small f of x, is obtained by differentiating the cumulative distribution function, capital F of x. This concept can be extended to two random variables, x and y, and you can obtain the joint PDF by partially differentiating the joint CDF with respect to x, then with respect to y. The order of differentiation again does not matter. So this dou sign that you see here, it's called as the dou sign. Dou, it's pronounced as dou, and it means partial derivative. So first you will differentiate with respect to x by considering y as constant, then you will differentiate with respect to y considering x as constant. Now let's look into some properties of joint PDF. So your joint probability density function is always going to be greater than or equal to 0, and that is because the joint CDF is an increasing surface. And therefore, the partial derivatives of the joint CDF with respect to x and y is going to give you another function which will always be greater than or equal to 0. So small f of x may go up and down, but it will always be greater than or equal to 0. Just like the case of single continuous random variables, when you integrate the PDF from negative infinity to infinity, you find the area under the curve, which is always equal to 1. Should you double integrate the joint PDF from negative infinity to infinity, that should always give you 1. So such a concept is used to find hidden constant in the joint PDF. So use this concept to find any hidden constants in the joint PDF. In the case of joint probability density function, you will be interested in evaluating probability that x and y belong to a particular area. To find such a probability, what we do is we double integrate the joint PDF over that area. Notice the similarity with single continuous random variables. In the case of single continuous random variables, we are interested in finding the probability that the random variable x belongs to a particular interval, and therefore we would integrate the probability density function over that interval. In this case, we will be interested in finding the probability that the random variables x and y belong to a particular area. So extending the concept from single continuous random variables, here we need to double integrate the joint PDF over that area. You can also obtain the individual probability density functions of x and y from the joint PDF. To obtain the marginal PDF of x, we integrate the joint PDF with respect to y from negative infinity to infinity. Please pay careful attention to these limits of integration. It's from negative infinity to infinity. Now, depending on your PDFs, this may change a little, and I'm going to show you how, but this is the primary formula, from negative infinity to infinity. Essentially, what we are trying to do here is we are trying to disregard the variable y from the joint PDF. So whatever function that will be remaining, that will be the marginal PDF of x. Similarly, the marginal PDF of y is obtained by integrating the joint PDF with respect to x. So we are disregarding x from the joint PDF to find the marginal PDF of y. So we are going to use these concepts to extract the individual density functions of these two random variables, x and y. Now, let's also discuss the concept of event independence. Now, if you recall from the very first unit, two events A and B, they are independent if and only if probability of A and B gives you probability of A times probability of B. Now, this uses a concept that if A were to be independent of B, any information about B should not alter the probability of A. So that should give you the probability of A. Probability of A given B is written as probability of A and B, or probability of B, by applying the conditional probability formula. And therefore, probability of A and B is equal to probability of A times probability of B for two events A and B that are independent. This concept can be easily extended to the joint PMFs and the marginal PMFs as well. Two joint random variables, x and y, if they are discrete, they are independent of each other if the product of their marginal PMFs gives you the joint PMF. Similarly, two continuous random variables x and y, they are independent of each other if the product of their marginal PDFs gives you their joint PDF. So this is a simple extension from unit 1 to this unit where we explore independence of different random variables. In fact, the concept of independence helps us to model different situations. For example, recall an example that I gave you for the joint random variables with respect to finding the time it takes for the coronavirus pandemic to go away. And we represented that random variable with capital Z. which was equal to x, which was the time it took for the random variable, or it was the time that medical professionals took to devise a vaccine. And then we had another variable y, which was the time it takes for the vaccination to finally kick in. So we can say that z is equal to x plus y. If we have the individual probability models of x and y, and if we have a reasonable case to assume that they are independent, then the joint PDF of x and y can be written as the product of their individual probability density functions. Once we obtain that, we can find different probabilities for z. For example, what is the probability that z is less than let's say 5 months? So in this case, we are evaluating what is the probability that x plus y is less than 5 months. So the concept of independence plays a very crucial role in solving some joint probability problems, and we are going to look into some certain such examples as well. Okay, I think it's a good time to stop this lecturette right here. In the next lecturette, I'm going to show you how to solve probability problems with joint random variables using specific example. So the next lecturette is going to cover some examples where we'll devise marginal PDFs using the joint PDF and solve some probability problems. The probability problems using joint random variables requires a specific algorithm that is composed of these steps, step 1, step 2, and step 3. This video lecturette will get too long if I were to discuss it, so I'm going to stop right here. In the next lecturette, we'll pick it up from this point onwards. Adios, guys.